Okay, so the problem we ended with on the first video of this was this indeterminate product. And again, just as a reminder or a pickup for the spot we left off, if you plug an infinity into this, or negative infinity, you're going to get infinity squared, which is infinity, times e to the negative infinity, which is 0. So what you're going to generate here is infinity times 0. And that is considered indeterminate. We don't know what big times small is. Could end up being infinity, could end up being 0, or could be some number in between. And in order for us to figure it out, what we need to do is take and write this thing, just like we did with the difference one, either as 0 over 0 or infinity over infinity in order to apply L'Hopital's rule. It's a terrible infinity over infinity. So we're looking to create one of these two. And once you have that, then you can use L'Hopital's rule, which simply says derivative of top, derivative of bottom, evaluate the limit. The limit can go to any value, infinity, a number, it could be 0, which I guess is a number, but whatever, you get me. What that means is we either have to write this thing as x squared over 1 over e to the x, that's an equivalent expression, or we have to write it as e to the x over 1 over x squared. If you algebraically adjusted those, both would get back to the original expression. You could try either of them. And in either case, you can apply L'Hopital's rule, because in this first one, if you put in the negative infinity, you're going to get infinity over 1 over e to the negative infinity. So that's actually infinity over, if you flip this on the bottom, it's infinity. So you get infinity over infinity. Or here, you end up getting 0 over 1 over infinity, which is 0 over 0. And so you've created the two potential indeterminate forms by setting up a quotient, or setting up something where you've got division going on instead of multiplication. And I want to stress again, these are the uncommon cases. So these are not the common uses that the AP has for L'Hopital. They tend to just set you up straight away with 0 over 0 or infinity over infinity. However, there are these extension ideas, and it's important to explore those. So we need to choose one way to do it. And I think in the last video, I said, okay, we're going to choose this one. The reason I like that one is if we attempt to do derivatives with x to the negative 2, derivatives go down in power. So they decrease, which means the derivative of that thing would have an x to the negative 3. And e just stays as e. So we'd just be spinning our wheels on this one, and it wouldn't go anywhere. And you could eventually convince yourself of that. And if you want a little extra credit project for yourself, it's not literally extra credit, just for personal, satisfaction type of deal, go ahead and start taking derivatives on that one, and you'll see pretty quickly where it goes. On this one, though, on this first one, if we take derivatives on it, will actually productively go somewhere. So I'm going to look at that. And again, we're taking the limit as x goes to negative infinity. I'm going to write that in there just so I don't get confused like I have in the past. If we do the derivative of the top, so we apply L'Hopital's, that's 2x. If we do the derivative of the bottom, we get negative e to the negative x. That is still an expression that if we plugged a negative infinity into, we would get infinity over infinity. We actually get negative infinity over negative infinity, but the positive negative sign is not the thing that we're focused on. So then we'll apply L'Hopital's rule again. So here's one application of L'Hopital's. You can apply it as many times as you need, as long as you're productively getting somewhere. And in this case, we take the derivative of the top, we get 2. Derivative of the bottom is e to the negative x. So plug in our negative infinity now. 2 is just a 2. On the bottom, then, we get e to the negative of a negative, so e to the infinity. So we get 2 over infinity. Well, 2 over infinity is 0. So this limit, as x approaches negative infinity, is 0. And so specifically up here, this limit, put a square around that, is 0. So this indeterminate form, when we do the infinity times 0, what that's saying is the little 0 is actually much more 0-like than the infinity is really big. And I know that's a kind of hard abstract idea to get around, but that is what's going on with L'Hopital's rule. So again, what you're looking to do is create infinity over infinity or 0 over 0. And we looked at the trig expression that you could subtract infinities. We looked at this indeterminate product. The last case, or the last class of things, are the indeterminate powers. And the indeterminate powers are kind of cool. So indeterminate Indeterminate powers. Yeah, that's a tough one. The indeterminate powers are when we take a limit and we get 0 to the 0 power, infinity to the 0 power, or 1 to the infinity. In either of those cases, we don't know how to evaluate them because in each of them, again, it's a limit. So 0 represents something big, or small rather, infinity represents something big. And each of them give us something where there's a push and a pull between the power and between the base. And even in the case of the 1, the 1's not really 1, it's a number close to 1. Well, if you're close to the 1 but you're bigger and you go to infinity, you'd be getting bigger. If you're close to the 1 but you're smaller, you'd be getting smaller when you multiply it by itself an infinite number of times. So we have to come up with a way to sort this out. And again, really uncommon. These are kind of the asterisk type cases, but they happen. They're of note and they do occur. So let's look at an example. Let's do the limit as x approaches 0 of 1 minus 2x to the 1 over x power. And if you look at this one, when 0 goes in, we have 1 on the inside of the parentheses, and we have 1 over 0 in the power. So that is 1 to the infinity. And again, it's going to depend on, there's a push and pull between what that 1 is supposed to do when you take it to any power, and what infinity is supposed to do to any number when you multiply it by itself that many times. So in that case, to make this into L'Hopital's rule, again, we have to create one of two things, always, 0 over 0 or infinity over infinity. We have to create that before we can do the derivative rule. So to create that, and this is where this one falls in that asterisk category of more challenging problems that the AP tends to shy away from. This is the expression we're looking at. We're looking at this function and we're saying what happens when x gets close to 0. So to evaluate that function, one thing I can do to it that preserves equality is I can ln both sides. You might remember this from when we were doing logarithmic differentiation. What that allows for is I can pull the 1 over x out front as a multiplier, and that's just one of the log rules. And then I can write this right-hand side as ln 1 minus 2x all over x. And I'm going to take and apply that limit just on the right-hand side. I'm going to do the limit as x approaches, approaches 0 of this expression. Now all of a sudden I've got L'Hopital's. I've got a 0 on top, the ln of 1, and I've got a 0 on the bottom. So that meets the requirement for L'Hopital. So that meets the requirement for L'Hopital. So now in this case, I'm going to say, okay, let's go ahead and take the derivative. If I take the derivative of the top, I get 1 over 1 minus 2x times the derivative of the inside, which is negative 2. Take the derivative of the bottom, I get 1. And again, I got to be better about this. I'm going to keep that limit on there. So that's going to be negative 2 over 1 minus 2x all over 1. But anytime you divide anything by 1, you don't need to write that. Now at this point, I can plug that 0 in, and I'm going to get a negative 2. Okay, so we have to be careful here what we just found. What we just found was we took the limit of both sides of this thing. The limit as x approaches 0, the limit as x approaches 0. So by taking the limit of both sides, what I'm left with is, hey, here's what the ln of y is going to. So again, the ln of y is on this side, and on this side I said this thing's actually worth 2. So the ln of y is going towards negative 2. Well, that's the ln of y. What I'm after is just y. I want to know what happens to y, what happens to this thing. So I have to get back to a y equals. So I'm going to e both sides. And this is the trick or the thing that makes it a lot more challenging. That means I'm left with y equals e to the negative 2. So this is the additional step when you're dealing with indeterminate powers. After you use the logarithm, you have to return it to its y equals form. And to do that, you're going to e both sides to undo the act of the y, or of the ln. So we used the ln to move the power out front. We applied the limit. And then we said, well, that's actually what the ln of y is worth. So now we need to get back to y. And to undo that process, we're going to e both sides. And this then ends up being the answer or the value of this limit. So all the way back up here where we said we had this 1 to the infinity. That 1 to the infinity is actually worth e to the negative 2, which is obviously impossible to see just looking at it. You couldn't say that's 1 over e squared, which is what what e to the negative 2 is. There's no way you could connect those two without using some more robust form of mathematics, which is what this represents. So that's L'Hopital's rule. I'm going to ask you to do some practice problems with it from the textbook, because the textbook actually has quite a few good ones. And I'm going to ask specifically you do the odds so you can check answers in the back with relative ease. The one note I wanted to make before I send you off to do a little bit of work was there are times where L'Hopital's rule breaks down. If you try to apply it to problems that don't require it, you potentially are going to end up with a wrong answer. So L'Hopital's rule only works for infinity over infinity or 0 over 0. And obviously we saw some forms that you could manipulate to create that, but this is when you're using it. As an example, and this is the final thing I'll ask we talk about before I send you to do some practice, we've got the limit as x approaches pi of sine of x over 1 minus cosine of x. If you saw this sitting and you thought, oh my gosh, there's a fraction, and I know when I see fractions, a lot of times I do a L'Hopital rule, and you didn't actually think about this or evaluate it. You just plowed right ahead with L'Hopital's. You take the derivative at top, you get cosine. So this is if we use L'Hopital's rule. You take the derivative of the bottom, you get sine. If you then pop a pi into that expression, you get cosine of pi over sine of pi. And cosine of pi over sine of pi, well, cosine of pi, let's see, that would be a 1. Is that right? Cosine of pi, we're starting, oh no, that's a negative 1. We're down at the bottom of the cosine curve. And then sine is 0. So you get negative 1 over 0, which is this negative infinity term. And actually, in my problem, I left off, I put a little negative right there, approaching pi from the left. If we approach pi from the left, still get a negative 1 up here, but then you get a positive small number on the bottom, and that's kind of a semantics thing, but it's important in terms of determining the sign on this. But if you did it all this way, it'd be wrong. So this is garbage. It doesn't work. It doesn't mean you took the derivatives wrong, but what it means is you can't apply L'Hopital's rule in the first place because what you have is actually a working limit. So you actually have something where you can evaluate the limit face value. If you put sine of pi in right off the bat, and you do 1 minus the cosine of pi, so you just apply the limit straight away. Well, sine of pi, that's 0. Cosine of pi, what do we say? That was a negative 1, right? So then we get 0 over 1 plus 1, otherwise known as 2. And 0 over 2 is just 0. That means the limit as x approaches negative pi is 0. We didn't need L'Hopital's rule. So it only will work, guaranteed work, if it's infinity over infinity or 0 over 0. If it's any other format, you potentially are getting led astray by just looking at the derivative comparison. So that's a minor distinction, and the AP doesn't attempt to trick you with that. But it's just good to know that you don't trick yourself with it. So if you see a limit that presents in fractional form, attempt to plug this thing in first. Verify it's L'Hopital. Verify it's infinity over infinity or 0 over 0, and then go ahead with doing derivatives. But otherwise, again, what I'd like you to do is some practice problems out of the textbook to get a little more experience with this. And you can see the document that outlines the odd set of problems.